Alright folks, today we're going to look at ionic and covalent compounds. We're going to look into how we come about their names from either the elemental symbols or from the actual names and generate the elemental symbols. For the most part, we understand, whether you know it or not, covalent compounds. Covalent compounds are a heck of a lot easier to figure out the nomenclature. The ionic compounds are ones a little bit more complex. So we're going to spend a little bit more time on those. And I think I have all of like 2 slides to cover the covalent compounds, which is a nice trade-off. All right, so ionic compounds build off of that whole idea we saw in the past with the valence electrons. So what happens with our metals is they generally lose electrons. So, and that accounts for all of our metals, the blue ones. They like to lose electrons, become positively charged cations. All right, those strongly charged cations get attracted to the nonmetals, which give up or accept those electrons and become negatively charged. So that happens in ionic bonds all the time. You have a positive charged ion, cation, and you have a negatively charged anion that are attracted to one another. Now, weaker than that, but actually a little bit more interesting, are the covalent bonds. The covalent bonds are sharing of electrons. So it happens between 2 nonmetals. So what they'll end up doing, since both of them want one more electron, in this case, they had 7 electrons, they want one more, they end up sharing a pair. And that's why they're in there like in the middle. Those 2 are being shared. So this nonmetal on the left sees 2, 4, 6, 8 electrons, and the one on the right also sees 2, 4, 6, 8. They share those electrons. Now, we're going to look more into this idea later on and figure out how to draw structures, but in this chapter we're just looking at the distinction between the 2 and how to name them. Alright, the ions that we see, so the metals, are going to form the cations, and we have a few nice rules that we're going to start with. Everything in group 1, and that's on the periodic table, everything in group 1 that's blue, likes to give up 1 electron and become positively charged. So lithium becomes lithium plus, sodium, sodium plus. Everything in group 2 likes to lose 2. So magnesium will form a positive 2 ion. And that's what this is talking about here. Now we're going to see some others down here, but we're looking at just group 1 and group 2 right now. The nonmetals are going to lose the electron, and fortunately they have a nice predictable pattern as well. So everything in group 15 that's under nitrogen likes to gain 3 electrons, so they like to form the 3 minuses, and 2 minuses, and 1 minuses. And you can see that right on the periodic table. Everything here that's yellow, fluorine, chlorine, bromine, and iodine, likes to gain 1 electron, so they like to be negatively charged. Oxygen and sulfur and selenium like to be -2, and sodium and phosphate like to be -3. And no real exceptions to that. Now, selenium's not here because it does something else and it's rare, but we're just going to ignore it. And ignore the aluminum for just a moment. We're going to come back to that. All right, so when these combine, or when they lose the electrons, they're going to form an ionic compound. Now, ionic compounds are just a mixture of those cations and anions. Now, we will never show the total number. We're going to show you what the ratio is. What I mean by that, sodium chloride, which is something that we're familiar, is made up of sodium ions and chlorine ions. Well, they actually mix in equal amounts. The number of sodiums is exactly equal to the number of chlorines, and we could predict that based on the fact that the charges are the exact same. So when we write the formula for sodium chloride, we're just going to have NaCl. We're going to combine them so those charges balance out. Now, a statement about ionic compounds. They are very strong attractions, and because of that, these guys end up with very high melting points. Sodium chloride, for instance, you can get your stove as hot as you possibly can, put sodium chloride on there, it's going to stay a solid. You have to get up to like 800 degrees Celsius to melt that stuff. Really, really hot that it's needed. And almost all of our ionic compounds are high like that, and some of them even much higher than that 800. All right, so when we form them, I just mentioned this loosely, that we actually put 1 sodium and 1 chlorine because the charges are the same. what we're going to always do is have a situation where the overall charge of the ionic compound is 0. So if I were to take that sodium, for instance, and instead of chlorine, move to the left on the periodic table and grab an oxygen, which likes to be a -2, likes to be a -2 because it's in that 2 rows over. Well, to balance out the charges, I need more sodiums. Oop, that plus looks terrible. Giving us a formula of Na2O. Now, when we write the formula, we're always going to write the metal first, and then the nonmetal. And we're going to use those numbers to tell us how many that we actually have. And I got a few examples. There's our sodium chloride. The sodium likes to lose an electron. The chlorine likes to gain it, and we get NaCl, sodium chloride. If I have magnesium, since magnesium likes to be the +2 and chlorine likes to be a -1, a +2 and a -1, we're going to have to add more chlorines to balance out that charge, giving us MgCl2. And one more of these, sodium sulfide. Sodium likes to be +1. Sulfur likes to gain 2 electrons to become a -2, so I'm going to need 2 sodiums to neutralize that, Na2S. Now this slide I skipped over was how we go about naming them. This is actually quite simple. We're going to see that the metal, or the cation, gets listed by its name, whatever the element is. And then the nonmetal, or the anion, we just change the suffix to IDE. So, and we saw that before. What do we call this stuff? Well, not that one. And sodium chloride. It's not chlorine. We change the suffix to an IDE. This next one, sodium oxide. Sodium metal gets listed first, or stated first. Oxygen, the suffix gets changed to IDE. And then our 3 examples, sodium chloride, magnesium chloride, and sodium sulfide. Relatively simple, relatively straightforward. So let's come up with the formula and the name when we mix barium with chlorine. All right, and we see that it got 2 positive for barium and a negative for the chlorine. So I'm going to need to double the chlorines. And that makes barium chloride. Now what kind of throws people off at first here is they're used to hearing things like carbon dioxide. You hear those prefixes to tell you how those atoms are in there. We'll see those prefixes get used for our nonmetals, the covalent bonds. On ionic compounds, we don't say that. We don't tell you it's 2 chlorines with a di in front of it. We just say barium chloride because that's what's in there. The formula came about because the charges are on there, but there's no variation here. There's not a chance for that chlorine to be anything other than a negative, and there's no chance for the barium to be anything other than barium 2+. So barium chloride must be BaCl2. All right, so practice these when you get a chance, but you're going to see a charge, and you're just going to mix them together and nullify the charges. And the only one in here that's terribly complex is that bottom one. I have Mg2+ and N3-, but we'll see that these common multiple of these is 6, so I'm going to need 3 magnesiums and 2 nitrogens. But name-wise, that is just magnesium nitride. All right, let's do some more complex things to this. So the reason this chart up here just said group 1 and group 2 is because those are the only 2 that are fixed on their charges. What I mean by fixed, come back here to this weird thing that I just skipped over here. That middle section of the periodic table, there's only 4 atoms on here that have only 1 charge. So aluminum, for instance, it's always +3. Zinc and cadmium are always +2, and silver is always a +1. All of the other blue elements on the periodic table, mine there's this slightly light blue, every single one of those has more than 1 positive ion they can form. Now there's always one that's most common, but I don't need you to know that. just need you to be aware that there's more than one, because we're going to have to somehow tell you this. What this translates to is like these irons here. There's actually 2 iron oxides. So oxygen was that -2, so there is an FeO. Oh, well, FeO. And that's just where the iron is a +2 and the oxygen's a +2, or -2. There is also one where the Fe is a 3, so that makes an Fe2O3. Now, technically, if we followed the old rules, we'd call these iron oxide. But they both can't be iron oxide. And this was an interesting little dilemma to figure out names a long time ago, because both of these things are elements that were known to ancient man. Coming out of the Bronze Age into the Iron Age, the alchemists at the time figured out how to take both that iron oxide on the top and the iron oxide on the bottom and turn them into iron. This one is a little bit more common. It was an ore known as hematite. This one less, but mainly because it's not found in many places. It is found, though. Oddly enough, these two were found mixed together, and this is one you might have heard about. I know you'll get the prefix. Magnetite. It was a magnetic rock. It was either found naturally magnetic, or it could be made magnet if you got it close enough in the magnetic field. Now, I wrote that formula how we see it typically now, but if we go back to like when John Dalton figured up those rules about the law of constant composition and whatnot, he would have had this written down as Fe3O4, where he just combined these two. But again, it's just an iron oxide, so we're going to have to do something to actually distinguish these to make sense out of it. Now, we're going to do something kind of neat, and it seems obvious now that we know what this is made out of. Knowing that, like this first one, the Fe was a 2+, and the oxygen was a -, and this one was a 3+, and this is a... Ooh, I got that. Oxygen's always a 2-. We're just going to put Roman numerals to say what the charges are. Now this one down here, we don't name it when it's based on that. When this gets named, this is actually called iron 2, 3 oxide, to stress that it's a mixture of both those. It's just how it's put together gets a different overall structure when they crystallize together. Alright, so turns out everything here in the middle, you're going to need a Roman numeral to tell you what the charge is. And that's the only distinction. That's the only thing that's really different. It happens a lot, and it's always just a Roman numeral. Anything is normal. And we don't bother to go with like their old ancient names. So tin was known as that Stanius and ferrum and such. We use those symbols, but we write the English name that we're familiar with. Alright, so how do we put this together? We're using those Roman numerals, and we're going to have something like this. So I have the iron there with sulfur. I know from looking at the periodic table, because sulfur is right here under oxygen, it likes to be a -2 all the time. So if there's 3 of those, this would give me a total of -6. That means these 2 irons need to give me +6, so each one of these is a 3. Therefore, iron 3, sulfide is my name. Now the next one, copper oxide, CuO. Oxygen's always a -2. Therefore, this copper must be a +2, giving us copper 2 oxide. As simple as that is, what ends up throwing people off more than anything is when they have to turn the name into a structure. It kind of helps to start with those basic ones, because there are a couple steps we have to do that are obvious when we're doing it with a name like this. So potassium, for instance, and sulfur, we're going to get those names, and then we're going to get from the periodic table what their charges would be. Potassium's here in group 1, so it's going to be a positive ion. Sulfur, they're underneath oxygen in group 16, going going to be a -2. And to neutralize that, we just have to have twice as many potassiums to get those charges the same, giving us K2S. All right, follow the same steps when you have that Roman numeral. And common mistake people do is they see that 3 and write iron 3 chloride. And that seems like, okay, that I can see why that happens, because iron 3 chloride. That's how you'd say that. All right, but the iron 3 isn't telling you how many there are. It's telling you the charge of the iron. You don't tell the charge of the chlorine because it's always the same. It's over here in group 17. So it is always going to form a -1 ion. Therefore, iron 3 chloride is FeCl3. All right, so which one of these is copper 1 nitride? Well, we just look at the periodic table and we figure out the charge of the nitride, nitrogen, would be -3. And I don't need to look at the periodic table for copper 1 because that 1 tells me the charge. Therefore, copper, I need 3 of them to give me copper 1 nitride. Now, oxygen, probably remember this by now, it's always a 2 negative. So lead 4, I would need 2 oxygens to every 1 lead. All right. When we name these, we're going to come back to this wonderful thing. I have this nice little flow chart here. Our cations always follow into 1 or 2 categories when there is a metal involved. They're either in that group 1 through 13. So actually, I'm going to change this to say group 1 and 2. Ooh. 1 and 2. And then zinc, silver, cadmium, forget about the ammonium for a second, and aluminum +3. Those are the other ones fixed. So it says here on this thing that group 3 is, but the only one in group 3, it's actually 13, that is fixed is the aluminum. All these others can be +3, but they can be something else as well. So we're going to just distinguish that. Everything else that's on there, you'll need a Roman numeral. All right, now it says NH4. Now, NH4 is made up of a bunch of nonmetals. That seems like it shouldn't be here at all because we were saying metals over here. Well, it turns out it should say cations. Now, it's fair to say metals because all metal ions are cations because they lose those electrons and become positively charged. But it turns out we have a class of compounds called polyatomic ions. Now, all that means is it's more than one atom combined, but they're stable enough they can exist as ions on their own. And that was what I skipped over here. So we have a bunch of these things that are called polyatomic ions that do things nice and behave together. Like, for instance, the biggest reason that, I'm going to go back to the periodic table here, that we didn't have any carbons with ionic compounds is mainly because there's not many carbides. You don't see sodium carbide too much. It does exist, it's just not very stable because the carbon reacts with the oxygen around there and it very easily on its own turns into carbonate. And that's where a large amount of the natural sources of carbon are that's outside of life. They're just trapped in carbonates all over the planet. But these other polyatomic ions, and you'll see a lot of them are just the nonmetals mixed with oxygens. We find them all over the place, but they're nice and stable, and they exist like that. I'm sure you've heard of phosphates. We use them in fertilizers and the phosphate chains in you. It's part of ATP. Nitrates are the same type of thing. Hydroxides, you might have heard them mixed with like sodium and potassium. So sodium and potassium hydroxide are cleaning agents or bases. But we see these all over the place. And there's a whole bunch of polyatomic ions. Now, tables like this one are like in your book, and I give you some in the instructions on the test. Now, you'll notice my list is a lot shorter, and it is all these that end with ATE. So carbonate, chlorate, chromate, nitrate, permanganate, phosphate, and sulfate. Now the reason I don't give you a complete list is because there's kind of a simple rule to figure out what an ite is. So look at this. I got the nitrate there. Right below it is the nitrite. Look at the only thing that's different. Just one O. Chlorate and chlorite, it's one O. If there was a carbonite, you would expect it to be CO2, 2 minus. Charge stays the same. Sulfate to become sulfite, you lose an O. And phosphate to become phosphite, you lose an O. So on this, if I ask you what chlorite is, for instance, you know you're, just removing an oxygen from there. And then on the periodic table, above and below chlorine, back up here, are we call them the halogens. Well, chlorate has a sister or a family member with bromium and iodine. Fluorine doesn't do these, but we can add to this BrO3 minus, just change the chlorine to a bromine, and you have bromate. And it seems made up iodate. Doesn't that sound like a made-up word? Well, it kind of is, but it was made up to follow along this the family line here. All right, but we will use these things, and they form ionic compounds because these are ions. So something very neat, even though ammonia is made up of nothing but nonmetals, and we'll do a carbonate, is a bunch of nonmetals as well. These two can go together and form, and I'm going to have two of these ammoniums, ammonium carbonate. Ooh, that C looks terrible, doesn't it? And you notice how I put that ammonia in parentheses? And I didn't double the nitrogens. I didn't go into H8. I actually did in H4 too. Well, that's how we do this with polyatomic ions. If we need to multiply them or add some, we are going to do those subscripts like we did before, but we're going to keep our polyatomic ion in parentheses so you know it's specifically ammonia. Because look at this. If I were to write into H8CO3, that could be this, but it also could be the nitrogens and hydrogens are connected differently. This is specifically telling us it's definitely ammonium. So that's why we write it like that. That's why we use those parentheses. Because there's a possibility that is something else. And I'm going to write it like this. Else. With a big, huge question mark because we're not sure. It's just that there's so many atoms they could be put together differently, and it might be a nonmetal. And therefore a bunch of covalent bonds. Alright, so when we apply this, it is very simple. We're going to figure out what that thing is, and we're going to name the same rule. So NaNO3, sodium nitrate. Potassium with the SO4, that's that sulfate. HCO3 is typically called bicarbonate, but you also see it called hydrogen carbonate. The bicarbonate is just telling you it's HCO3. You see that with, I'll go back here up to my polyatomic ions list. Sulfates and sulfites, there are bisulfates and bisulfites, and they just have a hydrogen with them. But both of those, you generally see hydrogen sulfate or hydrogen sulfite far more. So this is kind of interesting. This chart kind of shows them, and I'm going to just highlight this because this is more commonly found bicarbonate, but these guys, it's more commonly found with that hydrogen. Now, part of the reason that is, let's think about these weird rules. What do you think we'd call this? Sodium bicarbonate. Anybody ever heard of sodium bicarbonate? Yeah, it's baking soda. Oh, I just wrote sodium carbonate. I dropped my... But that's a little bit more commonly found as a prefix on that. Bicarbonate to distinguish it. I'm surprised we haven't kept with the bisulfate and bisulfite because it keeps you from having to write hydrogen. It's just we generally don't. We see the hydrogen sulfate and hydrogen sulfite. Alright, and then the last one here, it's got that ammonia with it, so ammonium phosphate. Now something interesting, you notice how these suffix names are just what those polyatomic ions are called? Before, when we did like sodium with Cl, we said sodium chloride. We changed that suffix to that IDE. Well, we're not changing any rules, we're just pointing out that when it's a polyatomic ion, we name the polyatomic ion what it is. Now the biggest reason we did that, rather than change this, if I'd called this sodium nitride, just change that to the same suffix, and then asked you to create it, you would have actually had sodium and then just nitrogen, because that's what nitride was called. So sodium nitride is specifically without that polyatomic ion, and this is telling you there's a polyatomic ion. The ATE suffix and ITE kind of tell you that. Alright, so Roman numeral polyatomic ions, we've got this all together now. And these happen a lot. Biggest reason we're adding them now is because if you look at the names of these, you might have recognized the names on some of them, but you definitely understand what they're talking about over here. So you might not have had first-hand experience with radioplaque medium. That basically means that this is this type of stuff they give people to inject or drink, and then when you x-ray that person, you see it. It actually shows up on actual x-rays. But as that might not be that common, but I'm sure you've heard of plaster cast. Sure you've heard of antacids. So a lot of these are things we've seen and use. And that's pretty much why we had to learn how to name them. Alright, so let's practice naming. We'll just do a couple of these. We're going to do the top one and actually D, and I'm specifically picking on D for a reason. Alright, magnesium with the NO3. So we've got a couple things we're going to do. Periodic table, we find that magnesium to figure out what that charge is. And then we either have to have all that memorized or use it. And the NO3, fortunately, is on that periodic table. On there with the polyatomic ions. It's right there. That is nitrate. Alright, now I wrote that +2, but the big thing to point out is, being that it is in group 2, when we're writing down the name, we're just going to write out magnesium. And there won't be a Roman numeral, because it's one of those that doesn't have the variation. So this is just magnesium, magnesium nitrate. Now the reason I skipped down to D that I wanted to cover is because it is Fe. And if I go to the periodic table for the iron, it's there in that lighter shade in that middle. It is one of those that has variable charge. So I know I'm going to write down iron, and I know I'm going to have a Roman numeral in there. Alright, so how do I figure out what the charge is? Well, the SO4 listed there is one of our polyatomic ions. It's the bottom one here. SO4 2- is sulfate. So I know this is iron something sulfate now. Alright, but that means that this is a -2. There are 3 of them, giving us a total of -6. So those 2 need to counterbalance it. That means these are iron 3s. And we just do all the combination of things we've done before. We're just going to, instead of using just the periodic table to get us our charge, we got to figure out what the charge is of those polyatomic ions. Now, I do want to point something out. If you try to figure out the charge of PO3, for instance, just by looking at the periodic table, it's not going to work out, because all those are actually negative, and nothing will make sense yet as to why the combination of 1 phosphorus and 3 oxygens gives you phosphite. I don't have it here. I have phosphate, but phosphite is PO3 3-. You're not going to make sense that is why it ends up as a 3- yet. So it is beneficial to have the polyatomic ions on that periodic table and just look them up and figure out what that charge is. Okay, moving on, because we can actually do that. Let's recreate one of these. We're going to do the first one and the last one, because it combines all of our steps. So potassium bromate. Now, potassium is on the periodic table. It's in group 1. So we know that potassium is going to just be K+. I got a bromate. This is one that's not on the polyatomic table, but bromine is in that family as chlorine. And I know it has chlorate. And this one asked about bromate, so I know it's going to be a similar structure with just the chlorine changed to a bromine. The charge will be the same. So potassium bromate is going to be KBrO3. And then our last one, E. I don't need to figure out what the charge of iron is. It tells me. I just got to figure out what nitrite is. So back to the family on the periodic table. I got nitrate as NO3 minus. So since we remove an oxygen to make a nitrite, nitrite must be NO2 minus. And to balance out those charges, I'm going to need 2 of those nitrates, giving us FeNO2 2. All right. I have plenty of practice on these things, but we actually gone over this. Nice little summary here. The anions typically don't give people as many problems because you're able to pull off those charges right on there. What does create problems on that anion side is those polyatomic ions. Now, we covered a lot of them, but there's a huge number of them. Matter of fact, even the ammonium ones, you're going to see in the medical field we take advantage of it. So if you've ever seen a long drug name, and at the very end of it you just see the letters HCl, all that means is somewhere in this big huge molecule is a nitrogen. And that nitrogen has got now 4 things on it, making it like this ammonium ion. Now, it's not necessarily 4 hydrogens, so that's why we're not going to call it ammonium. We're going to call it an amine. But these amine salts actually change a lot of properties. So what happened, the reason the medical field has done this, or the doctors or the researchers have done this, whatever this molecule in the block is, it was insoluble. It would not dissolve in water. I'm just going to write does not dissolve. Now, that's not necessarily a big deal, but if I want it to be something you can take orally, I need it to dissolve. Well, if it's got that big nitrogen on it and I can react it and turn it into this, I will turn that into an amine salt, and they are always water soluble. It really doesn't even matter how big they are. Now, technically, we see this even on the streets. And what I mean by that, I know you've heard of cocaine. Well, cocaine is kind of like what's with the HCl. So it'd be cocaine, HCl. It's a salt, but when you snuff it off your nose or put it in your mouth, it dissolves enough, and that creates that cocaine high. Well, crack is smoked. You heat it up and you cook it. Well, if you tried that with this, because this is a salt, an ionic compound, it has a ridiculously high melting point. And if I put it on like a cigarette and cook it, I've just got hot crystals of cocaine. They won't do anything. So what they do is they'll take their cocaine and treat it with a base of some kind. Suddenly that turns it into what's more of the raw cocaine itself. Suddenly it's a lot more organic-like. It's no longer water soluble, but it burns really well. And that is what allows crack to go in like it does. But so, chemistry for the streets. As a chemistry professor, I think I'm required to know these things nowadays. But I always thought that was kind of neat that we see this on drugs, the HCl. And it's just so we get some solubility properties. We'll explore some of that later chapters when we're talking about some of the bigger amine compounds. All right. I have plenty of test questions on this type of stuff, so make sure you're familiar with this, and I have videos on that, so if you have any questions, fire them towards me. All right, let's look at our covalent molecules. Now, generally speaking, a covalent molecule is when 2 nonmetals overlap in such a way that they share electrons. So a hydrogen only has one electron. It'd like to have none or two. If it has two electrons, it's going to behave like it's a helium, which is, in this last row, very inert, very stable. So in a covalent bond, that's what ends up happening. Two hydrogens that get together, those electrons being in between get shared, and each one of these hydrogens thinks it has two electrons. Now, on majority of our nonmetals, those covalent bonds happen when there's a lot more electrons. Fluorine, for instance, is very similar to what hydrogen does in the sense that you have one more electron you need to get you to that full shell, because it's one away from that neon. It just wants one electron. So you get two fluorines near each other, they overlap, and they share those electrons. We generally draw it like this. The covalent bond is, that line is representing two electrons, but they're being shared. So the fluorine electrons see those 6 electrons plus those 2. So it sees 8 electrons. Now it thinks it's got the same as neon. And the other fluorine does the same thing. Thinks it's like neon because it's got 2, 4, 6, 8. Now what's weird is, we're going to see this a lot, that those outer electrons, we're here at that last row, they like to gain one more. So they all like that. This row, they like to gain 2 more. This one, they like to gain 3 more. But they like to get to 8 in that outer shell, like their noble gases. We actually call it an octet, and we say there's an octet rule. We say that whenever you're making a bond, in a covalent bond, you want to get to the point where each atom thinks they have 8 electrons. And we're going to do that more in a coming up chapter where we do our Lewis structures and draw out what structures are, even some more complex things. But we've seen this before. I mean, even people outside of chemistry have seen a structure to represent water where they have the 2 hydrogens and oxygen and some lone electrons. What's what they're drawing? You're drawing the structure of water. We have the 2 electrons there, 2 electrons there, and then a pair of electrons, 2 pairs of electrons, giving us 8 electrons around that oxygen. So the oxygen is following that octet rule. And each hydrogen, not really following the octet rule, but it's still got 2 like helium. It's the only one that doesn't really do the octet rule, yet we say it's following the octet rule. That's just because it only bothers to get as many as helium. Alright, but when we do this, because covalent bonds happen in such weird ways, we see multiple different combinations. What I mean by that, 2 that you probably are familiar with are carbon oxides. We have carbon dioxide and carbon oxide, or monoxide. Now, generally speaking, the mono gets left out a lot. Because if we were supposed to use it always, we would have called that monocarbon dioxide and monocarbon monoxide. Typically, we use the mono when we stress something. We want to draw attention to it. And we kind of do on carbon monoxide because it's toxic. I mean, if you get exposed to too much of that, it screws up the hemoglobins in us and it stops them from working. You can die from exposure from carbon monoxide, even if you're in a room full of oxygen. But carbon dioxide has to get really high to be dangerous because our body can handle that because we make it. Alright, so we use the mono when we stress it. Other than that, we use these prefixes. But what I'm wanting to point out now is if I wrote, I'm just going to make something up that doesn't exist, C2O6, there is at least a possibility that's a molecule, at least temporarily. So we might actually have to see it, and we would name it using these prefixes. We would call that dicarbon, carbon, and 6 is hexa. I didn't leave myself enough room. Hexaoxide. And regardless of whether or not it's a real molecule, that is just how we follow these rules to name it. We're going to look at those, that formula, and change the prefixes to tell it. So S with 3 oxygens, sulfur, trioxide. You can say mono if you want, but typically we only use that to draw attention to things. We most of the time ignore it. P4S3. P is probably the weirdest. because the prefix is actually tetra. It's not like quad or one of the ones that might be a little bit more common. It's tetra. So tetrous phosphorus trisulfide. Now something I didn't mention, but I want to point out here, was whatever is listed last, notice how I changed that suffix to IDE. It's not saying sulfur, it says sulfide. So very common we rechange that. So 1 silicon, 4 chlorines. Silicon tetrachloride. Cl2O7 dichlorine, so that can't be right. Heptaoxide. Now, neat thing is, that's really it for the covalent molecules. We follow those prefixes. Now, we break that down very quickly, and we don't use this too much beyond these, because once it's more than 2 atoms, it gets a bit trickier. Like, I'll just give us a for instance. We have, I'm going to draw the structure of it. This guy might not know what it is from the structure, and if you do, that's pretty impressive that you remembered this. But you've all seen this. This is vinegar. Now, specifically, it is acetic acid, and ironically, it's most often written as a molecular formula as HC2H3O2. They combine all that. And you will occasionally, especially as you get closer to the organic chemistry realm, see it written more like this. Now that last way, it's drawn very similar to how I have the structure. A carbon with 3 hydrogens, and a carbon with 2 oxygens, and then an H. Now, reason it's drawn like that first one there, that acid part of it is telling you one of those H's, at least one of those H's, comes off relatively easy. That's what acids are. They just are something that loses H's easy. Turns out it's this one. So the C2H3O2, that is this part of the molecule. Oh, my circle looks terrible. But that's that part of that molecule, and then just an H. Alright, but you notice how I wrote this down, and at no time did I say this is hydrogen dichlorine trihydrogen dioxygen. Because as soon as we get complex, this nomenclature stops happening. We really just do this nomenclature for when there's 2 elements. And we sometimes draw attention to it just to actually scare people. Like if I followed these rules, you would call this dihydrogen oxide. But if I wanted to scare people, dihydrogen monoxide. And if you're ever really bored, look up DHMO on the internet and find all the crazy ways people have actually explained that DHMO, which is just water, is a scary thing. Because yes, technically, if you stay submerged in it for like 5 minutes, you're probably not coming back from that, right? Everybody knows that. You don't stay underwater for 5 minutes. But if I call it DHMO, it sounds scary. Like for instance, did you know that they still make baby food with DHMO in it? Doesn't it just sound scary for me saying that? Yet if I said, you know they still make baby food with water, no one would care. But call it DHMO seems scary. So there's internet memes on that. Just kind of funny stuff. Alright. You will generally see stuff like this, where I just give you the structure, and I'm asking if it's ionic, covalent, and I want the name. And it's going to be a good mixture of things. So let's do the first one on this, and we'll do D. So SNOs. That is going to be a covalent molecule. Now, it's possible that it could be a polyatomic ion, but SO3 by itself is not. That is like the NH4, where this is the other ones that pop up. All right, so this is just covalent. So this is sulfur trioxide. We use that suffix or that prefix to tell us how many there are. And then D, I see the CO3, but this has got copper with it. That is a metal. This is a polyatomic ion. This is an ionic compound. Now, the CO3, being our polyatomic ion, you need to have the charge memorized, or I'm going to look here. And carbonate is CO3 2-. I have one of those. And I have 2 coppers to balance that out, so these need to be +1s, giving us copper 1 carbonate. Piece of cake. Alright, like I said, I have the little practice test going. I have a bunch of these as sample problems, but let's try to go backwards on one of these. So I'm doing the same thing. Is it ionic or covalent? And then give me the formula. So this first one I have calcium nitrate. Calcium is one of my metals. Nitrate is one of my polyatomic ions. So using that periodic table, we would find that calcium is a 2+, and nitrate is an NO3-. I would need 2 nitrates to cancel that out. So this is ionic, because a bunch of ions, and it is calcium nitrate. And just like the last one, we're going to do D here. D, dinitrogen tetraoxide, or tetroxide. Dinitrogen tetroxide. Bunch of nonmetals. This is covalent. All right. Thank you, folks. Let me know if you have any questions on this stuff, or if I could expand on anything.